Let me tell you about the universe in my mind. When we cast our gaze into the deeper cosmos and study the tiniest particles, we continuously encounter strange and astonishing ideas. They inform us how the universe operates and hint at what might happen in the distant future. From the possibility of time-reversing cameras to colliding hidden dimensions, these theories constantly push the boundaries of science and stretch our imagination. Each mystery poses questions that cannot be answered with simple solutions, and in exploring them, we begin to see the universe from entirely new, mind-bending perspectives. Let's delve into these cosmic mysteries now. Tonight, in our Universe series, we will decode galaxies, the cosmic background, the physics of light-heavy ions, and ancient sound waves to pinpoint the moment the universe truly illuminated. It's a long story, but we'll begin it in a dream. Before we start, don't forget to like and share. The Sachs-Wolf (SW) effect captures the faintest signals in the universe, using an almost invisible mechanism to map unseen forces and the universe's most ancient epoch. Imagine you are looking at a picture taken over 13 billion years ago, but this picture is not a clear image. Rather, it is composed of the extremely tiny temperature variations in the cosmic microwave background (CMB) radiation. This is the CMB Sachs-Wolf effect, named after the two scientists, Rainer Sachs and Arthur Wolf. It captures the minute differences in temperature and brightness caused by gravity. It acts like a fingerprint, recording all the traces left by photons as they travel across the vast cosmos and are influenced by gravitational effects. These subtle CMB temperature fluctuations provide crucial clues for understanding cosmic inflation, an ancient epoch of time dilation during which the universe expanded at an unimaginable rate. A key point of the Sachs-Wolf effect is that it demonstrates the so-called gravitational redshift, the process by which light continuously loses energy as it escapes a gravitational field. As photons from the early universe traverse vast clumps of matter, they must contend with the gravitational field. In climbing out of these gravitational potential wells, the photons lose a portion of their energy, and their wavelength is slightly stretched. These subtle changes reveal where those powerful gravitational forces once resided. This temperature map is essentially an extremely detailed gravitational potential map. It allows scientists to glimpse the cosmic large-scale structure that dominated the formation of galaxies. Without the Sachs-Wolf effect, we would have virtually no way of knowing which matter and energy-rich regions, in the distant past, ultimately shaped the appearance of the observable universe today. The Sachs-Wolf effect also informs us about the signature left by dark energy in the universe. Dark energy is a mysterious force that is causing the universe's expansion to accelerate. The strength of this effect changes in different locations as the gravitational potential wells in the universe evolve. When photons from the CMB pass through clusters of galaxies, they gain a tiny boost in energy, and then lose that energy upon exiting the gravitational field. If there were no dark energy pushing the expansion, this energy gain and loss would largely cancel each other out, and the pattern of temperature variation would be relatively predictable. However, scientists have observed small but real deviations in these temperature maps. These subtle asymmetries suggest that dark energy is altering the way photons interact with gravity. The Sachs-Wolf effect allows us to clearly perceive the presence of dark energy in an indirect way, even though we have never directly observed it. Beyond elucidating dark energy, the Sachs-Wolf effect also carries the earliest imprints left by cosmic inflation. During inflation, space stretched rapidly, exceeding the speed of light. Quantum fluctuations, these extremely tiny, random energy jitters, were frozen into the expanding space. These fluctuations became the subtle differences in density across the universe, which later evolved into the blueprints for galaxy clusters. The Sachs-Wolf effect is capable of capturing these early density variations, enabling scientists to trace the universe's growth from its initial quantum level all the way to the colossal structures of today, which contain thousands of galaxies. These minute cmb temperature differences also help us measure whether the universe is spatially flat, a question concerning the geometry of the cosmos. When we say the universe is flat, it means that on very large scales, space behaves more like a nearly planar surface, with little significant curvature. The measurements from the Sachs-Wolf (SW) effect support this view, as these small temperature fluctuations align very well with the flat universe model. If space were highly curved, the temperature patterns would show noticeable anomalies in different directions and locations, whereas the observed pattern is relatively consistent. This further reinforces the hypothesis of a flat universe. This understanding affects our comprehension of the large-scale gravitational behavior of the universe and influences our predictions regarding the ultimate shape and future evolution of the cosmos. The SW effect has an interesting extension known as the integrated Sachs-Wolf (ISW) effect. When dark energy dominates the universe's expansion, the gravitational potential wells between clusters of galaxies change over time. As photons traverse these time-varying potential wells, they gain or lose extremely small amounts of energy. These energy changes manifest as additional, subtle temperature fluctuations in the CMB. By studying the ISW effect, scientists indirectly observe the presence of dark energy, not by seeing the dark energy itself, but by observing how it modifies the gravitational potentials on cosmic, large scales. This is somewhat analogous to feeling the wind on your body without seeing the wind itself. The temperature fluctuations within the SW effect also conceal clues about the missing baryon problem. Baryons are the components of ordinary matter, such as protons and neutrons. Theoretically, they should exist in the universe in large quantities, yet a portion of them is difficult to find directly in stars and interstellar gas. By studying the subtle variations in CMB temperature, scientists can infer where these baryons might be hiding. The fine structures in the Sachs-Wolf signal suggest that a fraction of the baryons is floating in the intergalactic medium (IGM) in areas that seem otherwise empty. This is like completing a piece of the cosmic jigsaw puzzle, filling in the long missing mass and structure. More intriguingly, some temperature variations in the Sachs-Wolf effect appear to form specific shapes, hinting at anisotropy, subtle irregularities in the universe's distribution across different directions. While the CMB as a whole is remarkably uniform, the overlaid Sachs-Wolf effect introduces a slight directional preference, leading to extremely subtle inhomogeneities in the sky. One particularly notable region is nicknamed the axis of evil. This is an unexpected alignment structure observed in the CMB data, challenging the traditional view of a perfectly random and isotropic universe. Such alignment could hint at large-scale structures we have yet to understand, or even suggest a deeper, hidden pattern within the cosmos. The quantum imprints left by inflation form a power spectrum in the CMB, and the Sachs-Wolf effect allows scientists to directly observe this spectral signature. This power spectrum illustrates the distribution of the magnitude of density fluctuations in the early universe, reflecting which scales or sizes of peaks and troughs are more prominent. This acts like a cosmic blueprint, mapping out where future galaxies and enormous cosmic voids will eventually appear. The Sachs-Wolf effect provides a unique window, allowing scientists to connect those initial tiny quantum random variations with the galaxy structures that span billions of light-years today. The minute temperature differences recorded by the Sachs-Wolf effect also serve as a cosmic time machine. It captures the state of the universe when it was only about 380,000 years old. As the universe continued to expand, the photons emitted during this era were stretched, redshifted, and are now embedded within the CMB radiation. This instantaneous snapshot carries the density, temperature, and even the faint traces of dark matter from the early universe. Dark matter itself does not emit light or radiation directly, but the variations in the Sachs-Wolf effect show how the gravity of dark matter alters the path of photons. Scientists can thus indirectly reconstruct the distribution of dark matter in the early cosmos. Certain clusters of galaxies and immense galaxy clusters cause particularly noticeable temperature depressions in the Sachs-Wolf effect. This mechanism helps scientists map out the large-scale structure of the universe, such as superclusters, those gigantic groupings of galaxies. When photons pass through these structures, the temperature fingerprints they leave allow us to gauge the gravitational strength of these cosmic giants. These temperature imprints also help us understand the morphology of the cosmic web, the vast network woven by galaxies and dark matter. One challenge in observing the Sachs-Wolf (SW) effect is that it is highly susceptible to contamination from foreground sources in the nearby universe, such as interstellar dust or radio waves emitted by stars and galaxies. Dust can obscure these faint temperature variations. Therefore, scientists must employ sophisticated filtering techniques to separate the SW signal from the complex background. These techniques are crucial because even a slight contamination can distort the results, thereby affecting our understanding of dark energy, dark matter, and the state of the early universe. The Sachs-Wolf effect is also an important tool for testing general relativity (GR). Einstein's theory predicts that gravity influences the propagation of light in the universe in specific ways, and the observations of the Sachs-Wolf effect are highly consistent with these predictions. This makes the effect one of the strongest pieces of evidence supporting general relativity on cosmic scales. Through this high degree of agreement, we gain a clearer understanding of the role gravity plays in shaping cosmic structures. However, if future data were to show significant deviations, they might signal that new gravitational theories beyond general relativity are beckoning. The density of dark matter also affects the strength of the Sachs-Wolf effect. The magnitude of the effect changes depending on the amount of dark matter in a given region. Scientists can thus use it to indirectly determine the distribution of dark matter. Although dark matter is invisible and cannot be directly imaged, its gravity subtly alters the path of CMB photons. This unseen but real influence allows researchers to map the approximate spatial distribution of dark matter and further understand its impact on galaxy formation. The temperature maps produced by the Sachs-Wolf effect are also excellent tools for calibrating telescopes. Astronomers use these extremely precise temperature fluctuations to fine-tune the sensitivity of their instruments. Once telescopes are calibrated to this exquisite degree, scientists can collect more accurate data from the CMB, and even capture fainter cosmic signals. This calibration repeatedly helps us push our vision further into the past, tracing cosmic history deeper. By continuously observing how dark energy influences the Sachs-Wolf effect, humanity has an opportunity to gauge the ultimate fate of the universe. Will the universe continue its accelerated expansion, or will it one day gradually slow down or even reverse course? If this effect shows subtle changes over time, it could imply that dark energy itself is slowly evolving. This would directly influence the universe's final destiny, whether it is eternally expanding and ripped apart Big Rip, or eventually cools into a silent, vast darkness Big Freeze. The Sachs-Wolf effect measures more than just gravity, it also allows us to see the primordial density fluctuations, the original seeds that later grew into stars and galaxies. These early density differences determine the subsequent arrangement of cosmic structure, demonstrating how quantum imprints slowly transformed into galaxy clusters and super large-scale structures during the expansion of space. Through these faint temperature changes, the Sachs-Wolf effect reveals the universe's evolutionary journey from extreme simplicity to today's complex diversity. Every minute temperature difference marks a place where gravity once drew matter together, ultimately weaving the galaxies and voids we see today. The X-ray filaments in the galactic center are among the most mysterious structures in our galaxy. These long, linear streaks, seemingly etched by energy, traverse the central region of the Milky Way, displaying powerful energy and anomalous patterns. These high-energy structures emit X-rays, exposing the extreme environment near the Milky Way's core, especially around our supermassive black hole, Sagittarius A*. Unlike typical supernova remnants, these filaments are long and narrow, and they align neatly along magnetic field lines. This indicates they exist within extremely powerful and highly ordered magnetic field environments. A distinctive feature of these filaments is that the gas temperature within them can reach millions of degrees Celsius, far hotter than the surrounding interstellar medium. This implies that the filaments are connected to processes of extremely high energy. When photons pass through these structures, the temperature fingerprints they leave allow us to gauge the gravitational strength of these cosmic giants. These temperature imprints also help us understand the morphology of the cosmic web, the vast network woven by galaxies and dark matter. One challenge in observing the Sachs-Wolf (SW) effect is that it is highly susceptible to contamination from foreground sources in the nearby universe, such as interstellar dust, or radio waves emitted by stars and galaxies. Dust can obscure these faint temperature variations. Therefore, scientists must employ sophisticated filtering techniques to separate the SW signal from the complex background. These techniques are crucial because even a slight contamination can distort the results, thereby affecting our understanding of dark energy, dark matter, and the state of the early universe. The Sachs-Wolf effect is also an important tool for testing general relativity (GR). Einstein's theory predicts that gravity influences the propagation of light in the universe in specific ways, and the observations of the Sachs-Wolf effect are highly consistent with these predictions. This makes the effect one of the strongest pieces of evidence supporting general relativity on cosmic scales. Through this high degree of agreement, we gain a clearer understanding of the role gravity plays in shaping cosmic structures. However, if future data were to show significant deviations, they might signal that new gravitational theories beyond general relativity are beckoning. The density of dark matter also affects the strength of the Sachs-Wolf effect. The magnitude of the effect changes depending on the amount of dark matter in a given region. Scientists can thus use it to indirectly determine the distribution of dark matter. Although dark matter is invisible and cannot be directly imaged, its gravity subtly alters the path of CMB photons. This unseen but real influence allows researchers to map the approximate spatial distribution of dark matter and further understand its impact on galaxy formation. The temperature maps produced by the Sachs-Wolf effect are also excellent tools for calibrating telescopes. Astronomers use these extremely precise temperature fluctuations to fine-tune the sensitivity of their instruments. Once telescopes are calibrated to this exquisite degree, scientists can collect more accurate data from the CMB, and even capture fainter cosmic signals. This calibration repeatedly helps us push our vision further into the past, tracing cosmic history deeper. By continuously observing how dark energy influences the Sachs-Wolf effect, humanity has an opportunity to gauge the ultimate fate of the universe. Will the universe continue its accelerated expansion, or will it one day gradually slow down or even reverse course? If this effect shows subtle changes over time, it could imply that dark energy itself is slowly evolving. This would directly influence the universe's final destiny, whether it is eternally expanding and ripped apart Big Rip, or eventually cools into a silent, vast darkness Big Freeze. The Sachs-Wolf effect measures more than just gravity, it also allows us to see the primordial density fluctuations, the original seeds that later grew into stars and galaxies. These early density differences determine the subsequent arrangement of cosmic structure, demonstrating how quantum imprints slowly transformed into galaxy clusters and super large-scale structures during the expansion of space. Through these faint temperature changes, the Sachs-Wolf effect reveals the universe's evolutionary journey from extreme simplicity to today's complex diversity. Every minute temperature difference marks a place where gravity once drew matter together, ultimately weaving the galaxies and voids we see today. The X-ray filaments in the galactic center are among the most mysterious structures in our galaxy. These long, linear streaks, seemingly etched by energy, traverse the central region of the Milky Way, displaying powerful energy and anomalous patterns. These high-energy structures emit X-rays, exposing the extreme environment near the Milky Way's core, especially around our supermassive black hole, Sagittarius A*. Unlike typical supernova remnants, these filaments are long and narrow, and they align neatly along magnetic field lines. This indicates they exist within extremely powerful and highly ordered magnetic field environments. A distinctive feature of these filaments is that the gas temperature within them can reach millions of degrees Celsius, far hotter than the surrounding interstellar medium. This implies that the filaments are connected to processes of extremely high energy. If this hypothesis holds true, the filaments act as time capsules, preserving a record of fierce events that have long since ceased, yet remain legible today. The filaments exhibit astonishing stability, despite being filled with high-energy particles and intense radiation, they do not rapidly disperse or disintegrate. This stability itself is evidence that a powerful magnetic field is maintaining order behind the scenes. In a tumultuous and chaotic environment like the galactic center, such long-lived structures are extremely rare. They provide scientists with a unique platform to study high-energy astrophysical processes up close over extended periods. The interaction between the filaments and the surrounding interstellar medium is equally important. In star-forming regions and within molecular clouds, X-ray filaments may deliver energy into the dense gas. This energy injection potentially alters the conditions for stellar birth. Some models suggest that the magnetic fields and energy of the filaments can compress molecular clouds, triggering a new generation of star formation, while others propose they can inhibit the collapse of gas, thus delaying the pace of new births. Since these filaments are almost completely invisible in visible light, humanity must rely on X-ray observatories like Chandra to capture the high-energy X-rays they emit. This also implies that many more undiscovered X-ray filaments may be hidden from view within the galaxy, awaiting revelation by future, more sensitive, and comprehensive X-ray surveys. X-ray data indicates the presence of hotspots within some filaments, areas where energy is more concentrated. In these hotspots, processes like magnetic reconnection, where magnetic field lines break and reconnect, releasing energy, may be actively occurring. The energy released in these regions can accelerate particles to near the speed of light, explaining the localized, extremely intense X-ray radiation. By studying these hotspots, scientists can observe, on a cosmic scale, magnetic reconnection similar to that which occurs in solar flares, albeit on a much grander stage with higher energy output. As these filaments pass through gas streams, they twist and bend, giving us a visual representation of how magnetic fields truly behave within the flow. These streams affect the way gas and dust move through the galaxy, which in turn influences the structure of the interstellar medium. By tracking the shape and changes of the filaments, scientists can study how magnetic fields interact with other forces to collectively shape the overall appearance of the galaxy. Some researchers believe that the X-ray filaments could be a source of cosmic rays. Cosmic rays are high-energy charged particles that traverse the galaxy, sometimes reaching Earth, where they subtly influence our atmosphere and impact satellites and technological systems. If the filaments are capable of accelerating particles to sufficiently high speeds, they might be injecting these particles into the surrounding space, feeding the galaxy's population of high-energy cosmic rays. This places the galactic center in a pivotal role for cosmic ray research. The large-scale arrangement of the filaments has also led some scientists to propose the existence of an ordered magnetic field grid in the galactic center. Multiple filaments are not randomly distributed but are aligned along a larger scale structure. This invisible magnetic network influences the flow of particles and energy within the galactic core, acting like an unseen skeleton that supports the paths and direction of energy. The combination of X-rays, strong magnetic fields, and high-energy particles is what makes these filaments exceptionally special throughout the entire galaxy. They serve as a reminder that the galactic center is far more complex and violent than the pale strip of light seen by the naked eye. Each filament is a story, telling of how magnetic fields concentrate energy, shape gas and dust, and maintain long-term stability in an extreme environment. By exploring the mysteries of these X-ray filaments, scientists are not just studying the high-energy events themselves, they are piecing together the history of the galactic center. The filaments are like lines of text scattered in interstellar space, recording moments of black hole outbursts, eras of magnetic field change, and their collision with surrounding gas and dust. The galactic cosmic background light (GCBL), often also referred to as the extragalactic background light (EBL) in the broader context of cosmology, is a faint glow that pervades the entire universe. It is like an extremely thin mist that permeates the space between galaxies, holding clues to the universe's earliest epochs, the residual light left behind when the first stars and galaxies were just being born. Unlike the light we observe directly from individual stars or galaxies, the GCBL represents the accumulated, fossilized light of countless ancient stellar systems. It quietly fills the cosmos, representing the sum total of light scattered into the universe as galaxies evolved over billions of years. One of the most fascinating aspects of the galactic cosmic background light (GCBL) is that it reveals the rate of star formation in the early universe. By measuring the overall intensity of this background glow, scientists can estimate how quickly stars were forming during certain epochs. Star birth experiences peaks and troughs during different cosmic periods. The variation in the GCBL's brightness acts like a historical curve recording the stellar production line. When galaxies experienced a burst of star formation during a specific era, the background light would be slightly brighter, allowing us a glimpse into that densely starlit time. Unlike the nearly uniform cosmic microwave background (CMB), the GCBL originates from the galaxies themselves. It covers a wide range of wavelengths, spanning from the ultraviolet (UV) to the visible light and into the infrared (IR) band. Each band corresponds to a different stage in a galaxy's life. Early stellar clusters, mature spiral galaxies, and violently bursting starburst galaxies all contribute a part of their light in their respective bands. The GCBL superimposes all of this, creating a cosmic-level optical archive that records how galaxies went from nascent to mature and gradually faded over vast stretches of time. Scientists sometimes refer to the GCBL as cosmic light pollution because this background layer interferes with our observations of fainter, more distant celestial objects. When astronomers attempt to locate the remotest, dimmest galaxies, they must first carefully filter out this background light by subtracting it from the observation data. Yet, this seemingly contaminating element itself harbors countless important pieces of information. The GCBL also preserves the traces of the epoch of reionization. This was a crucial period in cosmic history when the first stars and galaxies emerged, and their intense radiation reionized the hydrogen atoms, turning the previously murky universe transparent again. The faint residual light in the GCBL records how this process unfolded step by step. It shows us how early stars and galaxies fundamentally changed the universe's structure, illuminating a dark cosmos into the star-studded scene we see today. Some of the GCBL light may originate from the activity of primordial black holes. These black holes formed very early in the universe, and as they consumed gas and matter, they released energy, producing intense radiation. Although we cannot see what those black holes looked like at the time, the light they once emitted may have mixed into the GCBL, becoming an almost indistinguishable part of this layer of cosmic mist, silently telling the story of the universe's earliest black holes. When galaxies collide and undergo violent interactions, they trigger intense starbursts, leading to the rapid formation of a large number of new stars in a short time. These burst-like star formation events significantly increase a galaxy's light output during that period. This light scatters throughout the cosmos and eventually merges into the GCBL. Every galaxy collision acts like a shockwave of photons injected into the cosmic background. Over time, these traces superimpose to form an energy ledger, recording how many violent encounters have occurred between galaxies. The color and brightness of the GCBL also reveal the distribution of stellar types in the early universe. Just as we use the color of red giants and blue supergiants to determine their age and temperature, the redder or bluer bias in the GCBL reflects which stellar types were dominant during a particular period. If the background light appears redder, it might imply that older, cooler stars were primarily responsible for the light. If it appears bluer, it suggests that younger, hotter, massive stars were more prevalent. These subtle color variations act like a set of hidden barcodes in the cosmic night. For astronomical observation, the GCBL is both noise and an unavoidable background. The Earth's atmosphere also blocks certain wavelengths, making GCBL measurement from the ground more difficult. Therefore, space telescopes are particularly important, especially those sensitive to infrared light, such as Spitzer or the Hubble Space Telescope's deep-field cameras. They can measure this faint background light as cleanly as possible in an environment virtually free of atmospheric interference, helping scientists piece together an image of the universe in its infancy. The GCBL is not a passively existing layer of light, it continuously interacts with cosmic dust. The dust absorbs the light and re-emits it at different wavelengths, altering the appearance of the GCBL and making certain areas slightly brighter or darker. This interaction with dust creates a hazy effect in the intergalactic space and affects our assessment of the universe's transparency. The GCBL is also related to the so-called missing light problem. Models predict that there should be more light in the universe than what we actually measure. A portion of the light seems to be missing. The GCBL, with its faint glow, is likely part of the puzzle, potentially accounting for a portion of the total light budget that is difficult to directly isolate. By precisely measuring the brightness and spectrum of the GCBL, scientists are incrementally tracing where this lost light has gone. Different types of galaxies contribute light to the GCBL in their own ways. Some theories even suggest the existence of extremely faint or even starless galaxies that are not bright enough to be directly observed. Yet, they might add minute amounts of light to the background through residual thermal radiation or reflection off dust. These exotic galaxies might be distributed in the vast, empty regions between galaxies, difficult to detect with traditional observations, but possibly leaving a faint trace in the GCBL. Various high-energy events in the universe, such as supernovae and gamma-ray bursts (GRBs), also contribute their energy to the GCBL. Each violent explosion is extremely brief, but the light they emit propagates through the universe for an immense amount of time. When this light becomes sufficiently faint, it too merges into the GCBL, becoming an almost indistinguishable fraction of it. These echoes of ancient explosions might only be a faint streak of brightness in the background today, but together they piece together a complete picture of the universe's energy history. Long before humanity could directly measure the GCBL, theoretical models had already predicted its existence as a byproduct of galaxy formation and evolution. This process, where theory precedes observation and is later confirmed, is not common in astronomy. It suggests that our understanding of large-scale cosmic behavior is reliable, at least in some aspects. With the advancement of infrared observation technology, this light, once confined to equations, has finally emerged in the data. The GCBL can also be viewed as a tool for measuring the optical depth of the universe, that is, how transparent the universe is to different wavelengths of light at different epochs. Before the epoch of reionization, light had difficulty propagating freely through the cosmos, and the GCBL spectrum preserves the imprint of light absorption and scattering during that time. By interpreting this information, scientists can estimate the universe's transparency at various stages. The GCBL also retains clues about the universe's metallicity. In astronomy, metals refer to elements heavier than hydrogen and helium. These elements are produced by nuclear fusion inside stars and ejected into the cosmos during supernova explosions. Traces of these elements, such as carbon and oxygen, appear in the GCBL spectrum. These traces tell us how heavy elements, which lay the foundation for subsequent stellar generations and life, accumulated gradually in the early galaxies, moving from an initially pristine sea of hydrogen and helium to one enriched with heavier elements. The GCBL offers direct evidence of this process. As galaxies grow by accreting gas and dust, they also emit additional light, and some of this accretion-related radiation also merges into the GCBL. This makes the GCBL a record of how galaxies grew step by consuming matter. More accretion events mean an added, almost invisible layer of brightness in the background light. Quasars, these extremely bright active galactic nuclei, are also affected by the GCBL. When the light emitted by quasars passes through space filled with the GCBL, it may experience slight blurring due to scattering and absorption. This light smearing effect slightly alters the brightness and energy distribution of the quasars we observe. By correcting for these effects, scientists can more accurately measure the quasars' intrinsic energy. These corrections, in turn, necessitate a sufficiently clear understanding of the GCBL. The GCBL may even leave a trace in cosmic voids. Cosmic voids are immense regions almost devoid of galaxies, which should theoretically be extremely dark. However, the faint glow of the GCBL makes these voids slightly less dark. By measuring the background light in these voids, scientists can indirectly study the size and shape of these regions, as well as the distribution of invisible matter within them. The GCBL is sometimes called the cosmic twilight. It represents a faint afterglow left behind by galaxies that have continuously shone for billions of years, the light of countless extinguished stars that still lingers in the universe, a collective memory of once bright galaxies slowly cooling down. This layer of cosmic twilight light fills the naturally dark distances between galaxies, reminding us that all brilliance eventually settles into a quiet background. For many years, the magnetic monopole has captivated the curiosity of physicists. Unlike the magnets we encounter daily, which always have a north and a south pole, a magnetic monopole is a hypothetical particle possessing only a single magnetic charge, either a north pole or a south pole. If it exists, it would complete the last missing piece of the puzzle in electromagnetic theory, achieving true symmetry between electricity and magnetism. The realization of this symmetry would fundamentally change our understanding of the nature of magnetic fields. The idea of the magnetic monopole was first proposed by physicist Paul Dirac. He pointed out that the existence of even a single magnetic monopole in the universe would be sufficient to explain another intriguing fact: why electric charge always appears in integer multiples. This is known as charge quantization. On Earth, no matter how you divide charge, the result is always an integer multiple of the elementary charge, not some strange decimal fraction. If magnetic monopoles truly exist, they would constrain electric charge to exist only in specific units, making the relationship between the electric field and the magnetic field much tighter than we currently imagine. Theory predicts that the magnetic monopole would have an extremely large mass, far exceeding most particles we are familiar with. This means they would move very slowly through space. It also implies that if a magnetic monopole were to pass through certain materials, it would leave a relatively distinct trace. Unlike ordinary particles that speed by, leaving almost no mark, a heavy magnetic monopole would interact more powerfully with matter, carving a unique trajectory in detectors. This trajectory is like a fingerprint, difficult to confuse with other particles. If the magnetic monopole were indeed discovered, it would fundamentally change the way we apply magnetism. Imagine a future where magnets with only a single pole could exist, a completely new type of magnetic source. Every magnet today has both north and south poles, and one cannot simply remove one of them. The magnetic monopole, however, is a single pole existing independently. This would allow scientists to find entirely new ways to manipulate magnetic fields, potentially revolutionizing everything from fundamental physics and electronic devices to medical imaging and materials science. Theory also suggests that magnetic monopoles are extremely stable. They would not decay rapidly like some unstable particles. If they formed in the early moments of the universe, they might still quietly exist somewhere in the cosmos today. This makes the magnetic monopole a long-lived fossil, carrying physical information from the universe's earliest instance. Finding one would be akin to unearthing a particle fossil from the early Big Bang in real life. To search for this elusive particle, scientists have to look towards extreme environments. Some experiments seek magnetic monopoles deep underground or beneath thick layers of ice. In these low background noise locations, particle trajectories are more easily preserved. With less interference from cosmic rays and ordinary radiation, a magnetic monopole, if it passed through, would have a better chance of leaving a clear trace. Superconductors are also considered a stage for hunting clues of the magnetic monopole. In some theories, a magnetic monopole entering a superconductor would excite an extremely unique signal. Superconductors conduct electricity without resistance and are very sensitive to magnetic fields. If a magnetic monopole appeared inside one, it might form a stable magnetic vortex, like a single pole-driven magnetic field swirl forming within the material. Studying these anomalies could allow scientists to indirectly touch upon the characteristics of the magnetic monopole through experimental means. The existence of magnetic monopoles would also reveal certain hidden symmetries in physics. In the current standard model of particle physics, electric charge has a clear dual counterpart, but magnetic charge is absent. Introducing the magnetic monopole would truly balance electricity and magnetism in the equations. This is not only mathematically elegant but also suggests that the fundamental forces in the universe may adhere to a higher-order symmetry that we have not yet fully grasped. Some theories suggest that the magnetic monopole might even play a role in catalyzing proton decay. In the standard model of particle physics, the proton's lifetime is extremely long, making it effectively stable. If magnetic monopoles could somehow facilitate proton decay, it would mean that the stability of matter is actually linked to these rare particles. Such a discovery would not only shatter our intuition about the permanence of matter but also connect the magnetic monopole to the long-term evolution of the universe. Magnetic monopoles could also affect the relationship between light and the vacuum. Some hypotheses propose that the magnetic monopole might alter certain properties of the vacuum, thereby minimally changing the way light propagates in the vacuum, for instance, by causing the speed of light to fluctuate on extremely minute scales. If this effect were confirmed, it would indicate that the vacuum, which we perceive as empty space, actually harbors a much more complex structure, and the magnetic monopole is a key to unlocking this knowledge. In the field of quantum computing, the magnetic monopole may also play a highly potential new role. With its unique property of isolated magnetic charge, it might offer unprecedented control precision in quantum bits qubits. In systems that require extremely accurate manipulation of magnetic fields, the magnetic monopole could act as a natural magnetic needlepoint, helping humanity construct more stable and powerful quantum logic units. To simulate the behavior of magnetic monopoles in the laboratory, scientists have also created so-called spin ice crystals. In these artificial materials, the arrangement of electron spins produces monopole-like excitations. While these are not true elementary particle monopoles, they possess similar dynamic characteristics. Spin ice provides us with a miniature experimental stage where we can study the potential behavior of magnetic monopoles in a controlled environment. Another novel idea is to search for the traces left by magnetic monopoles in ancient minerals, such as mica. This common mineral's layered structure potentially preserves the trajectories of particles passing through over long eons. If a magnetic monopole passed through rock layers at some point during Earth's geological history, the damaged track it left might be preserved like a fossil within the mineral. By analyzing these ancient rocks, humanity might find particle evidence from the early universe buried in the Earth's crust. In quantum field theory, magnetic monopoles would appear in Feynman diagrams, interacting uniquely with other particles. These theoretical depictions show how magnetic monopoles would alter particle exchange and loop structures, entirely different from ordinary magnetic fields. By studying these theoretical pathways, scientists can predict various new phenomena that the magnetic monopole might introduce, even without direct observation. If the magnetic monopole were ever truly discovered, we would have to rewrite Maxwell's equations. In their current form, this set of equations does not include a term for magnetic charge. Once the magnetic monopole is found to exist, electromagnetic theory would be expanded into a more complete form, and the electric and magnetic fields would truly be unified within a symmetric framework. This is not just a change in the form of equations but a leap in humanity's understanding of the natural world. From the stability of matter to the behavior of light in the vacuum, from the high-energy cosmos to quantum computing, the magnetic monopole acts like a multifaceted key potentially inserted into the locks of many physics doors, waiting for us to find it and truly turn it. Spin-flip transition is one of the most peculiar and important signals in the universe. It originates from the most common element, the hydrogen atom, yet records the grandest cosmic structures. A spin flip occurs when the electron spin in a neutral hydrogen atom flips from being antiparallel to the proton spin to being parallel. This seemingly trivial change releases a photon with a wavelength of approximately 21 centimeters, the famous 21 centimeter line. This signal can travel extremely vast distances across the cosmos without being easily absorbed by other processes, making it a central tool in radio astronomy. Although this transition is extremely rare for any single hydrogen atom, an atom might wait tens of millions of years for one flip. The sheer number of hydrogen atoms in the universe is immense, and hydrogen is the most abundant element. Therefore, when superimposed, the 21 centimeter line is ubiquitous throughout the cosmos. Neutral hydrogen itself does not emit brilliant light in the visible spectrum, but in the 21 cm band, it reveals itself to us. Wherever there are sufficiently large clouds of hydrogen gas, we can use this line to map the distribution of hydrogen within and between galaxies. For regions not illuminated by strong starlight, the 21 centimeter line is virtually the only reliable tracer. The 21 centimeter line is so valuable because it can transport us back to the universe's dark ages. Before the stars illuminated the cosmos, space was filled with cooling neutral hydrogen. There was no starlight then, nor the brilliant glow of galaxies, only the subtle spin flip of hydrogen atoms quietly recorded the conditions. As the universe slowly cooled, this signal diffused throughout space, becoming a faint, time-traveling echo. When the first stars and galaxies appeared, their intense radiation began to reionize the neutral hydrogen. This period is known as the epoch of reionization. The 21 centimeter line plays a crucial role in observing this transformation. In reionized regions, neutral hydrogen disappears, and the 21 centimeter emission fades away. Consequently, the otherwise continuous distribution of hydrogen in the sky appears as holes in 21 centimeter maps. These holes mark the regions first illuminated by stars and galaxies, forming an evolutionary map of the reionization epoch. The 21 centimeter line is also a thermometer for cosmic gas. When nearby supernovae or active galactic nuclei (AGN) release energy, they heat the surrounding hydrogen gas, which changes the brightness of the 21 centimeter signal. Through this enhancement or reduction in brightness, scientists can infer the degree to which the hydrogen gas is being heated or cooled, and thereby determine how energy flows within galaxies and in the intergalactic medium (IGM). On a macroscopic scale, the 21 centimeter line also allows us to see the outline of the cosmic web. The cosmic web is a gigantic network composed of slender filaments of hydrogen and dark matter. Galaxies and galaxy clusters tend to aggregate along these filaments, forming denser clumps at the nodes. By mapping the spatial distribution of hydrogen, the 21 centimeter line gradually reveals this otherwise invisible cosmic skeleton. Only neutral hydrogen emits the 21 centimeter line. In regions intensely irradiated by hot, young stars, hydrogen becomes ionized and loses this unique emission capability. This creates blank areas on 21 centimeter images. Scientists can precisely delineate the edges of these blank regions to locate where star formation is occurring and assess how stellar birth is progressing throughout the universe. The 21 centimeter line is not only used within galaxies, it also helps us measure the rotation of galaxies. When we observe the 21 centimeter signal from hydrogen gas at different locations within a galaxy, we can deduce the velocity distribution of that gas, thereby obtaining the galaxy's rotation curve. These rotation curves reveal the distribution of mass within the galaxy, especially the presence of dark matter, because the visible matter is nowhere near. Sufficient to explain the fact that hydrogen gas in the outer parts of the galaxy maintains a high rotational velocity. Due to cosmic expansion, the 21 centimeter signal from distant regions is redshifted, its wavelength is stretched. By measuring the degree of this redshift $z$, we can calculate the distance to the corresponding hydrogen cloud, and thus know how early in the universe that observation was made. By mapping the 21 centimeter line at different redshifts, scientists can construct a three-dimensional map of cosmic history, showing the distribution and evolution of hydrogen gas across various epochs. That concludes today's knowledge sharing. I wish everyone pleasant dreams and a wonderful day. We will see you in the next installment.